Okay, let's try another example here. Basically, the previous example worked flow regimes, was a turbulent flow regime. This example is laminar regime. And we're going to wind up just changing this exponent from 0.33 to 0.6, it was 0.66. Now we're going to change it down to 0.33, which the flow in the lab is laminar. It means viscous. And the pilot plant's also laminar. We're going to show you two things, the importance of the flow regime, and then also accompanying that is the importance of this exponent value. Okay. So if we remove all fluid properties, constants, and geometric ratios from the correlation, the following basically is obtained. And this will lead to the rotational speed scale 2 being 5 times the rotational speed of scale 1. And what will happen is this becomes impractical. Our scale-up procedure essentially becomes impractical. And that's what we have there. To succeed at scale-up in this process, the equipment has to be changed to a scrape wall instead of a stirred pot. This changes the heat transfer correlation, may result in a successful scale-up. So I have an experiment for you to do. We were talking about kitchen analogies. I want you to go home and cook some pudding on the stove. In other words, I want you to take some real powdery pudding, preferably vanilla, and cook it on the stove. And you will see that we'll start out turbulent with milk. It will be essentially turbulent flow. And as the pudding cooks, it gets thicker. The viscosity increases significantly. And you switch in to the laminar flow. The implication of this, you can notice how easily it is to burn your pudding in the stove, the non-laminar flow. It also points to the importance of geometry. Okay, I'm going to show you this. The color, let's try red. Now, if you were to stir this with a regular spoon and the pudding is burning, you find that the contact point between the burning hot pot and the spoon is very, very small. Okay, so I would have a very inefficient surface removal. However, if I come in and cook and wipe down my surface, which might be a spatula type, let me redo that again, spatula type. Let's put the spatula over here. Okay. Okay, and then the surface of the pot will be right along here, right along there. So I get a very good cleaning action, a good removal of the pudding from the bottom of the stove with something that has a very large contact area. Whereas opposed to a spoon here, I have a very poor contacting area. The whole idea is geometry. Geometry is critically important. I mentioned earlier that you have a cup of coffee and you stir it with a single straw, right? That's fairly ridiculous. However, if I change geometry, say if I go with 5 straws in here, right, and stir with 5 straws, what literally happens is I have a significant improvement in performance. I've changed geometry. I've gone from 1 worker, so to speak, to 5 workers. So the idea is that I got very good performance with 5 straws. Whereas that single straw gig is pretty ridiculous. I mean, you know, stir a cup of coffee. Then if you go into some of these McDonald's, they'll put a little stirrer down here. That's fairly ridiculous as well. So I don't know if that happens in if you've seen one of those, but that's pretty bloody ridiculous. So anyway, go back. The important implication of this is the lab may have used inappropriate equipment. The lab has used the inappropriate equipment, which allowed for the burning to begin, which caused the burning to begin with. Okay. Now then, you got to recognize the political problems here. The lab is filled with very sophisticated, smart PhD type people, right? So there's a sensitivity problem. You might have to tell them that perhaps they're not using the best equipment. And, you know, there's a give and take on the politics there. You don't want to tell them necessarily. So on scale up, geometric similarity may have to be broken to get the process to work. It's very important to recognize. But the idea that the lab was using inappropriate equipment, that means you have the right to choose more appropriate equipment. It's a good engineering type step there. Lab equipment may not be the geometry that you should use on equipment, on scale up, sorry. If the lab equipment is having difficulties with the process, other equipment should be considered. Processing problems come from poor design. Okay, let's go on to something called agglomeration, or agglomerate or design. You have dust, and dust is causing you a lot of problems. One way to handle the dust is to agglomerate, form an agglomerate. A new product could be the agglomerated material. Dusting is done on a small scale pan agglomerator. Now, there's various types of pan agglomerators. A flat pan rotates at an angle. Powder is added, rolls in the pan. Powder forms balls. These grow to larger sizes that flow over the side. So let's ask ourselves, what's the objectives? The objectives is to make agglomerates, basically. On scale up, you want to make the same size of agglomerates. Now, agglomerates, you may have seen them in fertilizer pellets are agglomerates. You see oftentimes agglomerates in cooking as well. Anyway, what are the important aspects of the problem? Well, let's take a look. We jumped ahead there somewhere, didn't we? Here we go. Well, I jumped backwards. Sorry. I seem to have lost myself. Here you go. I found myself. Okay. Now, you have to realize that agglomerates are formed by rolling. You roll an agglomerate. The rolling mechanics of agglomerate in the pan becomes important. You take a very small seed, you roll over fine particles, the seed will pick up material and grow in a larger agglomerate. The process is like making a snowman or snow woman, right? So this would be for the pan agglomerator. Same sort of thing applies with the drum agglomerator. There's a competitive geometry that's possible. The reason why you don't want to use the drum agglomerator is recycles 4 times the quantity of fresh feed. That's ridiculous. So quickly you find that perhaps a pan agglomerator is the best equipment for the job. Drums are less so. So what process similarity do you seek? What are you trying to do? Okay, now this is going to take some creative thinking here. Actually, it's like a snowman, right? Or a snow woman. You're making a snowman or snow boy or snow girl. And basically, roll distance. Roll distance. The size of the agglomerate will depend upon roll distance. So, Process similarity exists when the seed agglomerate has the same roll distance, meaning the same powder content between the two sizes. Rolling distance S should be a function of rotational velocity and the residence time. Residence time is how long the material stays in the process. That's the good word, residence. And it's the hold-up volume divided by the feed rate. Anyway, if I take residence time and multiply by the velocity, I got distance. And distance correlates to size. So I should have a size equals, particle size equals the roll distance, or proportional roll distance. So to keep the same size on scale up, I want the same roll distance on scale up. So I have scale 1 equaling scale 2, right? I'm going to keep the same residence time. This is a statement that actually the feed rate on scale up is going to go up proportional to the volume, or the... Anyway, if I cancel out the residence times here, and here, I'm left with n theta 1 equals, nd1 equals nd2. On small scale and the size scales. Now, again, I know n1, I know n and d here on scale 1. I know what size I want to scale to, which is d2. So I can calculate the rotational speed of the pan. What's doing the work? Roll action. What's the controlling mechanism? Or roll distance. The roll distance determines the size of the agglomerate. What's the size of the job? This is determined by D2. So, what are the process physics and chemistry? What are the process flow regimes? Process physics is discussed. Chemistry has a lot to do with the binder selection, okay? Formulation question, basically. Whether or not the agglomerate actually grows, what's the percent moisture, should it be cured, to what point it should be cured, all this is information that should be already available. Now, flow regime is a little bit different here. Sliding material in a drum can actually slide. Doesn't have to roll. You can have a rolling, and then you can have the material centrifuge to the wall. Okay, these are the possible flow regimes. Hopefully the design will be in the rolling regime. Equipment flexibility will allow operational search for this regime. So you will start searching for that regime. Geometric similarity is assumed. Residence time doesn't appear to be a geometric variable, but it is. Residence time, hold-up volume, has hold-up volume. Hold-up volume is very key, very important geometric variable. So you come along and you go to the data, scale up, method is obtained to see what we get. So the judgment's made as to whether scale up is appropriate. The answer is yes, yes. Will it be a working design? It's certainly a good first step. Basically, this is the famous equal tip speed concept that floats out there. Oftentimes, people think that equal tip speed equals equal performance. Well, in many cases it does, and in many cases it doesn't. So we think we'll have a working design, and the answer is yes. The geometry is the same as small scale. Operating conditions, speed of the pan is fixed by the procedure above. Again, it's first step. Certainly looks like a good first step. So we'll stop there. We won't do plan Bs until we know that this one works or does not work. Other designs not needed, large-scale polymer can be specified. Additional concerns, okay. Particle systems are particularly difficult because of the variety of the particles, their shape and particle size distribution, their physics and surface chemistries. And agglomeration, a number of concerns arise, and these include whether the particles demix, if the powder is a mixture of different particles, whether there's sufficient seeds to generate the agglomerates. See, the seeds is a problem. Whenever you're dealing with solid systems, it's often a good idea to seed the process. Seeding the process lets you avoid, it could help you avoid problems. Unknown effects of binders and curing effects. Dealing with particle systems, seeding may eliminate or minimize the number of processing problems. Poorly performing particle systems may be improved if proper seeding is implemented. Processing above has left out important information about seeding concentration in the original small-scale study. This may be an important technical issue since the agglomerates start from a seed. Seeding is also an important consideration in any particle system when trying to control particle size distributions. Typically, when you seed something, you seed it with a certain particle size distribution. That often grows, the shape of the distribution remains the same, but it just moves to higher, larger particles. Often initial size distribution of seeds is just shifted to larger sizes and forms the distribution at the beginning and becomes the distribution of the product at the end of the process. Pin mixer should be added to generate seeds. Care should be exercised in using such vague quantities as residence time. Residence time based upon inventory volume will be misleading. You really need to figure out what the working volume is. Working volume is where the process is taking place. Residence time can be quite misleading, right? There's been a lot of work on residence time distributions, which, sort of like reading tea leaves. The important volume is the working volume. Inventory volume, which does not take part in the process, is fairly misleading and scale up. You take residence time, okay? You can go into a university, and here's the professor lecturing away. Student comes into the classroom, goes to the back of the room, and immediately falls asleep, sleeps the whole lecture through. At the end of the lecture, he gets up and leaves. Another student comes in, goes to the front of the room, stays awake, asks questions, pesters the professor during his lecture, all kinds of things. So he's learning. That's a working volume. The kid in the back of the room sleeping, that's an inventory volume. So it's very important to have the material take part in the process, right? Residence time is not necessarily a translatable quantity in scale up. Processing time is the time that the process needs to accomplish the objectives, and the quantity should be or has to be smaller than residence time. Anyway, let's talk about atomization. Next example is not so simple. It changes geometry is needed immediately for the design to have a reasonably working process, and design B, plan Bs are implemented. Okay. The example I'm starting now is atomization, and you do need to do a change in geometry here, and we do need to, plan Bs are instituted. Okay, so it's desired to increase the production rate from 2 pounds per minute to 10 pounds a minute using a pressure swirl nozzle. 2 pounds a minute, the atomization pressure was 30 psi. You're desired to keep the drop size the same between the two processes. Basically, it's relatively similar to each other. So keep the drop sizes the same on scale up. What's doing the work? Well, we have nozzles. Let's see if this is possible. Now you scour the literature. If you haven't noticed, we're going to scour the literature and we're trying to find the controlling mechanism. Now, if you scour the literature, you find out the drop size for nozzles is controlled by what is called the flow number, or mass flow rate divided by the square root of the nozzle pressure drop and liquid density. If the flow number is kept constant on scale up, drop size will remain constant on scale up. So literally you have over here scale 1 equals scale 2. That's what we have down here. Now then, we're going to cancel out, we're going to put in the 2 pounds per minute for 30 psi, and we put in 10 pounds per minute with the psi that we have to determine. What's the size of the job? The size of the job is 10 pounds per minute. What's the process physics? Well, it's fairly well understood. Atomization through a nozzle. We're going to assume geometric similarity with mass flow rate and pressure drop given. We have calculate the pressure drop as 750 psi. Originally, we started with 30 psi at 2 pounds a minute. Now at 10 pounds a minute, we have 750 psi. Now that becomes, that's basically not available at the facility, right? So we wind up having an equipment limitation. We don't have this pressure to be able to, scale up is not appropriate. So we have results accomplished, no. Can scale up be accomplished, no. Results reasonable, no. Will be a working design, no. So the next question is, what is the maximum pressure that we do have? And so we have 90 pounds of steam, or 90 pounds pressure drop, sorry. And now we are going from a mass flow rate of 2 to 3.49. In other words, we put in the 2, we put in the 90, and calculate the M. So we're looking for 10 pounds a minute. We can get 3.4 out of one nozzle, and now we probably need 3 nozzles. So in a sense, we're doing a scale up to 90 psi. Simultaneously is that we're adding more nozzles, or more, quote, workers. Pressure drop is the worker, and also number in this case, number of nozzles. Moving right along, let's try this one. Example of metal processing with varying objectives and plant acceptance issues, right? Here, it's desired to make a powdered addition to a batch of molten aluminum. The batch is being mixed by an impeller. This is done on a small scale, and the rotational speed for submergence of the powder into the molten aluminum was determined. Remember the powder being added in the Artie Barinko video? It floated on the top. Now we want it to be added, and it gets pulled into the batch. Well, scale up. Objective is incorporate the powder into the batch. What's doing the work? What is the controlling mechanism? Batch is being stirred with an impeller. Solid submergence is being sought. Flow rate at the surface pulls in the material. Process physics is the drawdown of the powder into the batch, and the surface velocities must overcome gravity, right? Chemistry is not important. Anyway, chemistry is not an issue. What's the process regime? Turbulent, we're going to assume. Now, we search the literature and read up on solid submergence. We're going to go ahead and assume geometric similarity. And here we go. By the way, the last one, the atomization, right? We broke with geometric similarity. We had small scale 1 nozzle. Large scale, we had 3 nozzles. We naturally had to break the geometric similarity concept. I wanted to point that out to you. We didn't fail, necessarily. Okay. Go right along here. So if we check the literature on solid submergence, we run across this the Froude number, or modified Froude number. and basically says that equal surface behavior should be obtained when you have equal Froude number. That's true. So, judgment's made whether this is appropriate, and the answer is yes, yes, yes. Unfortunately, when we did testing, casting and metal parts, aluminum metal parts, failed, basically. They didn't make good quality cast aluminum parts. So the scale up was done correctly, but did not provide expected results. So we're stepping into plan B now, see what we can do to salvage this scale up. Plan B, what was the real problem? Well, let's go back to what they said here. They said, unfortunately, the scale up did not make good cast aluminum parts, okay? What was the real process? The real process was to disperse the powder into the batch of molten aluminum. Submerging the powder did not disperse the powder. I mean, the powder went below the liquid surface, but it went below the liquid surface in chunks, right? To disperse the powder, equal power per volume on scale up is more likely the objective, right? If you research power per volume, well, you'll find it's involved with the creation of surface area, creation of drops and bubbles. And so saying a bubble and a drop is similar to a chunk of powder. It's very similar. You think of it as a bubble with powder in it. Okay. So equal power per volume is likely to disperse the powder. So you should be very careful about what your process and process objectives are, because you may achieve them. Okay. Little twist on this. Oftentimes, as I said, on scale up, the process changes. Well, it changed here. Various levels and at various steps of the process, the various traps exist, right? Scale up is not necessarily straightforward. Various traps at various levels at various steps in the above scale up. There's another twist to the molten aluminum batch, which further illustrates the difficulties. Scale up of the dispersion of powder was successful using power per volume between the two sizes. Unfortunately, another problem occurred after a successful scale up. Upon casting and cooling, the powder demixed from the aluminum. Cooling took a long time, and allowed the powder to either rise to the top or settle to the bottom, which can be referred to as demixing. Right. So although this wasn't a scale-up issue, initially it's now become a problem. It became a problem because we were successful. Demixing was not anticipated. Demixing from aluminum for several reasons. First, the powder had a lower density than the aluminum and started to rise due to this density difference. Second, powder always carries with it, unless it's in a vacuum, powder always carries with it some amount of gas. In this case, air, which caused the powder to float. So you had some powder to sink and some powder to float. Now, if you incorporated the powder under gravity, that may have helped. So we have the powder, air as a problem phase. Air is a problem phase. Okay, as simple as this is, well, let's go back here. Okay. As simple as this, there was an additional problem due to plant acceptance. Operators refused to rotate the aluminum part as it cooled. See, if you rotated the aluminum part, you could have prevented demixing. Okay? If you Foundry operators refused to rotate the molds with aluminum part as they cooled. And scale up eventually involves plant operation. The plant environment becomes important and should not be overlooked. The operators are the ones who are making the money for the plant, and so you can anticipate that you need their support. So there's a little political problem out there. Now then, let's talk about scale up of dryers. And in particular, talk about scale up of spray dryers. The desire to scale up spray dryers, serious question, is there sufficient design information available about spray dryers? In which case, direct design methods should be used. And I suspect there is inside the companies. I suspect they have a number of different designs that they've used and been quite successful. All they got to do is take down the old design that worked and then just rename it, sell it to you. Information is also likely to be proprietary and not available in the open literature. So closed discussions with the equipment designer and manufacturer may be helpful. Okay. The equipment designer may only have to repeat the previous design that was successful as far as the designer was concerned. Discussions also, as discussed above, may not be fruitful, and scale-up studies have to be initiated. Well, scaling objectives are kind of tough here because here you have drying. That's one thing you got to do. Spray drying obviously involves drying. The next thing is you tack on, you want to have the same particle size as you dry that you had in the lab. Okay, and then you tack on the same bulk density. Or you just want to keep bulk density the same and dry. Or you may want to keep the particle size the same and the bulk density the same. So these are many, many different variables. Okay. Equipment selection was not done in the lab. Drop formation of scale-up wheel atomization is used. Okay, we're going to use wheel atomization. Nozzles was discussed earlier. Wheels can handle higher flow rates in abrasive feeds. Wheels are non-clugging, low-pressure systems in which drop size is controlled by speed. Wheels offer much more flexibility than nozzles. However, wheels cost a lot. Flow regimes. Probably the best way of showing flow regimes is right here. You have direct drop production, right, sitting here. And here you have sheet formation down here. And then you have the drops being formed in the outer perimeter of this sheet. And so we have direct drop production sheet. And in between is this regime right here. And my question to you is several things about this regime I'd like to point out. First off, these are fairly uniform threads, basically. And they break out into fairly uniform drops, and as a result will give you fairly uniform powder particles. So from the point of view of uniformity, this is a winner. This is something you can buy off the shelf, by the way. Okay. The other question I pose to you is, have you ever run into this type of machine before? The question is your experience. And the answer to that may be yes, you have seen this machine before. It's just that you weren't necessarily sensitized to it. You were likely to see this machine before in the production of cotton candy. You could have seen it in a carnival or amusement park or along the coast. Boardwalk along the coast where there's a cotton candy machine. You looked in, you would see filaments being formed, and they were all pretty much the same diameter, oddly enough. And there's also a substantial money difference here with this regime. This regime produces uniformity, significant uniformity. As a result, can be quite quite useful in making uniform product, which then you can sell for a much higher price. Okay. If I was to try to make a uniform emulsion, what I potentially would do is I would run this machine in air. This is being run in air, and then put the droplets here through a falling liquid curtain, and eventually concentrate it up, and I would have a uniform emulsion. Regimes have subregimes. Like there's 4 different types of liquid sheets, 4 or 5 different types of liquid sheets. Drops and wheels can be designed to encourage uniform drop production. These regimes occur primarily with liquid slurries with very fine particles. Atomization for slurries where the particle size exceeds the drop size, you will have different behaviors, I'm sure. What's the controlling mechanism? Well, drop size depends upon drop formation mechanism, drop size, boiling process, particle size of the slurry if significant. The effect of particle size on the slurry and particle size made in the spray dryer is not clear, and will probably have to be determined by piloting studies for our example. Bulk density of spray dried particles is very important in packing costs. Low bulk densities are not desirable. That means you have a lot of volume but no weight. Bulk density can be influenced by wheel design. What happens at very high rotational speeds, wheels generate high flow rates of air. At such air flow rates, the wheel feeds become aerated, right? Drops then contain air, which affects bulk density. Changes in wheel design can affect feed, aeration, and the influence of bulk densities. Example of a wheel. What you do is you plug it right here with a bushing and cut down on the. This wheel rotates this way, backwards, counterclockwise. Right. In other words, as the wheel rotates, it fills up the entire slot here. And the reason why it wants to do that is it gives it a chance to de-aerate some of the feed. Studies should be investigated in a pilot plant. Aeration of feed is minimized by densification, forward-turning vanes, or partially plugged holes. Densification is de-aeration. Get rid of the air bubbles. To influence the drop boiling process, steam can be injected alongside the liquid feed. Go back here. Feed would be coming straight down on that and knocking off. Anyway, where were we in here? Find my place again. To influence the boiling process, steam can be injected alongside the liquid feed. This slows down the boiling process and changes the bulk density. Very good idea. Okay, it's also true. Not only is it an idea, it's a true idea. What are the process physics and chemistry? Well, we talked about process physics here. Talk a little bit about the chemistry. The process chemistry in this scale-up concerns primarily whether the drop can withstand the high inlet air temperatures without harming the product. The first thing you want to determine in dealing with dryers, or one of the first things, is what's the inlet temperature? And then basically you want the inlet temperature to be at such a level as to not harm the product. So you have to run tests on that. That has to be answered by scallops. Multi-level approach. I would, if I was to do the scale up of a spray dryer, I would do a multi-level approach. I would have a vendor do some studies for me with their spray dryers. I would do my own pilot plant studies. I would do my whole heavy literature search. That's true as well. Throw in local universities and starving assistant professors or professors who want to make a name for themselves, that sort of thing. So give them a challenge, give them a little bit of money, and you can go very far. Also, there are tollers. Tollers are people who work for other people. They charge a toll for the use of their equipment. Tolling is very useful. Universities, okay. Pilot plant studies should be initiated to answer product-specific questions. Previous designs and information from different equipment vendors should be obtained. Again, it's a multi-level approach. Vendor, pilot plant studies. Anyway, moving right along, control drop size. Well, drop size is the mass flow rate divided by the rotational speed. Mass flow rate divided by the rotational speed. This lead constant is another objective of your scale-up study. You want to figure out what that value is. So you put scale 1 to scale 2, set them equal to each other. This will give you equal drop size on scale 1 to scale 2. This relationship may not be true since the K values may not be the same between the two scales and for different equipment. The exponents may change with size as well. Simple engineering correlations cannot handle all aspects of scale-up. Very important point. Simple correlation does not contain the various aspects of the problem discussed above. There's no information about bulk density, feed aeration, or the effects of tooth geometries. At this point, judgment should be made as to how the scale-up should be conducted. Significant questions exist which satisfy pilot studies, which justify pilot studies. Unfortunately, dying with the attempt to control particle size and bulk density at the same time may be asking too much for one piece of equipment. Basically, drying and particle size may have to be accomplished in one unit. Another unit, you may have to obtain the bulk density. So oftentimes you would have perhaps drying and particle size, then you use a grinding operation after that to obtain the desired bulk density. The KISS principle. You should keep it simple. Keep it simple, sweetheart. Okay. In a university, you were probably put through the rigors of academics, but in industry, you should recognize that you would like to do things simple, in a simple manner. So you take something highly complex and break it down into simple steps. It's also necessary to follow one unit operation with one ops operation. This may appear to be ridiculous, but such equipment arrangements offer considerable operating flexibility, robustness, and nimbleness. See, the idea of following one unit operation with exactly the opposite unit operation, i.e., size reduction followed by agglomeration, or agglomeration followed by size reduction, makes sense because it adds versatility to your equipment. Okay. What's ridiculous is to expect one piece of equipment to do everything. Sort of like a carpenter. A carpenter will show up to your house to do some carpentry work, and lo and behold, the only thing he has in his toolbox is a hammer, right? That's not a good carpenter. He should have a hammer, a saw, a screwdriver, sets of wrenches, all kinds of things, so he will have flexibility in his work. Same sort of thing. You want as much flexibility as you can obtain, right? In failure, there is no flexibility, robustness, or nimbleness, only education, which brings up the point that failure should be recognized as an important step going forward. The learning curve on failure is very high. So you learn very quickly what to do and how to do it. Whereas if you're daydreaming back there in the middle sunny fields, you may not appreciate what the failure can do for you. Process understanding. Should be obvious that different examples of scale up given above. There's no universal facility out there which handles all types of scale up. The concept of a universal facility to handle all processes never worked well in the past. Individual equipment should be selected to fulfill the individual needs of the process. The universal facility to scale up all forthcoming processes will result in a number of failures. If process design is being done entirely from scratch, the facility should fit the process. The process should not fit the facility, right? So, the concept of a universal pilot plant is not appropriate for scale-up. So, central need for scale-up is good process understanding. The processes are speaking to you. Are you listening? Good process understanding is not available. Then risks are going to increase significantly. And good process understanding is not developed quickly. It's not developed quickly. So here we have our various problems that we worked. Example of problems. Some are reasonable designs. Some are reasonable designs after geometry change. Successful but wrong objectives. Successful but planned acceptance issues. And outcome, too many objectives couldn't be accomplished, all of them. So we have here the various paths or outcomes of a scale-up process. Here we just go track some of these. We go up this line here, wrong process objectives. MSA, modify and start again. And then practical design, MSA. Up here, reasonable design after geometry change, MSA, modify and start again. You have a reasonable design. Well, you take a look at that reasonable design and ask yourself how reasonable it is. Reasonable design, but plant acceptance issues. You scale up on the wrong mechanism. Too many objectives and poor process understanding. So down here we have start scale up. So there you have it. Scale down. Now, the methods for scale down are similar to those that presented above. However, in scale down, the objective is to mimic plant behavior on the small scale. Doing so, the lab pilot plant take on properties occurring in the plant. If there is poor mixing in the plant and scaled down, there would be no mixing in laboratory studies. Geometry, again, does not have to be the same, and just as there are processes which cannot be scalable to larger sizes, there are processes which cannot be scaled down either. So, all right. So I leave you with this joke, and it says, got a few problems going from lab scale to full scale commercial. In the background, you see the chemist with his various types of beakers and the construction worker. And they do an exchange of words there. References, of course, my books, and then Peach's book and Lefebvre's book on atomization. So you get Peach's book, you read right through it, or you read Lefebvre's book and read right through it. It's a wealth of information. Okay, we are now at 149 in the slides. I think there's 600 or 560, something like that, to go. So we may be a third of the way through, fourth of the way through, something like that. So let's understand the traps that can happen here. And the first trap we're going to say is the ln plus 1 trap of geometric similarity. So we're going to scale up traps and overcoming new traps. The ln plus 1 mistake is made often in scaling. First item to check is this mistake. Earlier, the concept of a worker was introduced. The concept of the worker may simply disappear. Excuse me. The concept of the worker may appear to be simple, but is often overlooked in the design. And one of the things, worker depends upon length squared. Perhaps it's an area. These examples are everywhere in chemical and processing plants. Heat exchangers, mass transfer, chemical reactions, separators, fermentation, crushing and grinding, agglomeration. Size of the job is usually L cubed. So this leads to worker being area, L squared, to the size of the job, which is L cubed, leaves you 1 over L. And and I should point out when L gets large, right, when this L gets large, the worker simply disappears. That's the important issue on scale up, is your worker disappears. Now let's see if that's true. Let's do just some simple calculations. Problem. Process is undersized. When L becomes larger on scale up, 1 over L becomes smaller. In many cases, at large L's, the worker disappears on scale up. If the worker disappears, the process fails. This usually happens for geometrically similar processes when the worker is an area and volume is the size of the job, right? So let's just take, we have the scale 1, 2, and 5. The worker is L squared, so we have 1, 4, and 25. Volume is L cubed, 1, 8, 125. So we have scale 1, which is very, very small, which possibly could be the lab. We have 1 scale up, doubling in size. We find out the worker per volume is now been cut in half. And over here at 5, the scale factor of 5, we have the worker at 0.2. If this would continue, the worker to volume would become 0. The ratio worker to the size of the job diminishes at larger sizes, and this is for geometrically similar systems. This is why geometrically similar systems are basically a mistake. You always want to improve the geometry as you scale up. You should never commit to a single type of geometry. You always want to have the material improve with scale up. Ratio changes the physics of particles as well. Switch is made from surface forces to body forces, right? So if I go here, I have surface forces here and I have body forces here. I can say at large areas, the body forces are dominating the surface forces. At large L's, the surface forces become negligible. So, often the worker geometric similarity is the area or length, and sometimes the worker may even be a volume. Just try heat transfer, right, as an example. Okay. Anyway, heat transfer is occurring through this jacket, small scale. This jacket is a jacket of vessel, small scale. It works fine. However, when you scale up, you often find the jacket for a large vessel is not adequate enough to heat and cool it, right? So this leads to differences between small and large scale heat transfer processes. On scale up, the jacket is not sufficient. The area of heat transfer is not large enough to accomplish the process objectives. Heat transfer is accomplished by using a jacket on the small scale. This problem often exists in scaled processes. Typically, if you ever get into this area, you have a desire to heat just a little bit more or cool just a little bit more. This means heat transfer included direct heat transfer, direct heat injection. This is probably one of the best ways of solving the problem. Is you cook with live steam, perhaps, or you inject heat with live steam. Pump around loops with heat exchangers, that's not so hot. Not so hot. Typically, pump around loops, you can't put enough through a pump in comparison to what the impeller is pumping. Bayonet heat exchangers may work well. Boiling works well to get heat out. Evaporative cooling, well, okay. Which is evaporation. These should be considered on a large scale when heat transfer is an issue. Natural convection is not important or noticed on the small scale. It may become important on a large scale. Anyway, again, natural convection, which is not important or noticed on the small scale, may become important on the large scale. So if I go back here, boiling takes away a lot of heat. Pump around loop, not so much. Direct steam injection would be a great idea to get the heat in, or maybe even put in inject liquid CO2. Something radical. Anyway, let's see what we got. Hoover Dam, survival in the cold. Hoover Dam conducted, it's in Arizona, just outside Las Vegas, right? They did one small batch of concrete. Then they did another small batch of concrete, another small batch of concrete. Each one of them were chilled with cold water. And after the concrete set up, they pumped concrete through the pipes. Survival in the winter in the cold is also a function of size. Small bodies will cool and freeze faster, much more rapidly than large bodies, right? Standard trick the Eskimos would do is if they were caught outside in a blizzard, they would kill a walrus, cut it open, and crawl inside. Liquid mass transfer. We have L squared. Liquid mass transfer, we got to recognize that L squared represents the dispersion process and L cubed represents the coalescence process. So we have dispersion versus coalescence. That's 1 over L. And you quickly find out laboratory studies are often said to be dispersion controlled or area processes. It's because the L is small for a laboratory. When you go to a plant, L is large and coalescence controlling. This one is coming to you from Merck, Rahway, New Jersey. The idea of settled solids works fine here for this chemical reaction. For this chemical reaction, the solids on the tank bottom are not even noticed. So if I was to try to scale up this process, right? See if we can go up here. I guess I got to go up here, sideshow. What I would want to do when I scale up this process is I want to make sure the solids go throughout the entire tank, right? And when I have that, I will have chemical uniformities, small tank and large tank. Large tank has no, everything is uniform here in the large tank, right? Grinding operations, basically you have an L squared and L cubed volume. Trap set. This is actually one of my former students, right? He had a grinding operation, worked fine, small scale, right? Basically worked fine, small scale. So he had this thing right here working really, really well. Uh-oh, gotta go back one. And on scale up, so he had a grind time, a small scale, 1 hour. He went to this size, right, large scale, maybe a factor of 3 or 4, and length, right, and he scaled up, and 24-hour grind time for here. If you would take pictures of a particle, the particle would slowly approach the grind wheel, and the next instant it was gone, right? So if you look at the movies on such things, you will find that it's around in this area where all the grinding takes place, right? It's a circular disc here. So what you want to do is you want to make sure you have large quantities of that grinding area, right? So to get those large quantities, you start stacking these things. So he didn't have a 24-hour grind time when he went in and put in the stacks of these. He also extended the impeller shaft down and put it one down there. So you increase the grind areas for the large tank. And the grind times that he had was reduced down from 24 hours to 2 hours, 1 hour. He was quite effective. So we had ineffective chemical reaction with solid solids, ineffective grinding with limited grinding discs. Let's see if there's other traps. Let's go to this one here. One area is flotation here, flotation. And basically it's an L squared trap here. And basically it represents another types of traps up here. Could happen in flotation, pipe flow, possibly in boiling reactors, gas, liquid situations, fermentation, that sort of stuff. Materials floated to the surface of the tank. Basically what happens, you have something like this. You have a big, huge tank, or excuse me, you have a small tank. You did all your flotation studies in this small tank here. Material would float to the surface, right? Oops, sorry. The material would float to the surface, okay? And overflow into the overflow weirs. Let's get a different color, what do you say? So the material would overflow in the overflow weirs or troughs, whatever, and be harvested. Okay? And the harvesting area would be the inside. Again, this is used primarily in the ore industry or the mining industry. They have very low-grade ore. They reduce the ore down to very fine particles of dust. They bubble oxygen or surface active bubbles through it. The surface active bubbles pick up the metal and carries it to the surface. And at the surface, it overflows into a weir and collected up. And everybody's tinkled pink, right? Now then, I go scale up, and I use geometric similarity. Oop, wrong way. I use geometric similarity, right? So, I actually want a pointer. Let's go here. I want a highlighter. Yeah, I want a highlighter with something darker than yellow. That should do it. So I have a very large tank with the overflow weir here. Collect the material that's overflowed. Sort of like what happened over here, right? Now what actually happens is the material would come up and gets floated to the surface. The minerals are sitting here at the surface. And this portion of the floating material overflows and goes to the weir and is collected and harvested. The other portion of this tank here just sits there. It never makes the overflow weir. And as a result, it falls back into the batch or into the tank and gets refloated again, and falls back down and gets refloated again, effectively floated again. The efficiency of this thing may be 100% over here. The efficiency of this thing is 20%. So I was given a lecture, a flotation lecture, down in Phoenix, Arizona. And supposedly, I don't know if this is true, but most of the mining in the United States, 80% of it's supposed to occur around Tucson, Arizona. Well, whether I know that or not, I don't know. Big, huge copper mines, I think, are down there. Anyway, so I was lecturing away. I was explaining this in the flotation course. Way in the back of the room, didn't have very many people. I think I had 12, 15 people on flotation. And kid in the back of the room, excuse me, I shouldn't say kid. This guy was about 55 years old. I was talking away up here. And he says, he's listening to me talk. He says, "Oh, no." So what that implies, I have no idea what he meant by "oh, no." But what it meant to me was perhaps he was operating like this for 50 years, or he's operating like this. Never really stopped to think about whether this material actually overflowed to the overflow weir. So the way you identify this situation is you want to basically put dye on the surface, right? So get me some color. So I take this dye and I put it on the surface up here and record it with time, and I can see that it's not being harvested. That's the first thing I would do. And then I would figure out what this distance was, right? Because this was a highly efficient one. Then I would choose another highlighter color. Let's try that color. And I would fill in, I would put a weir here, another weir, overflow weir here, maybe another one up here, maybe, a sneaker one right in there, one right in there, and one right in there, and there, and one there. Then I would be able to harvest the material in the center of the tank. So there you have it. There you have it. This size, in a sense, this size essentially being reproduced over here. I probably have to have one right in here too. Maybe one up here. So the idea of the size, this size here is about the same size as that. So in a sense, when I put in these weirs and fill it in, I'm doing repeated design. This works well, I repeat it. I repeat it all the way across. Right. But I certainly don't want to operate like this. Highly inefficient. Anyhow, let's continue on. So I'm looking for a good ratio of trough length to trough area, or froth area. Trough length to froth area. All right. Spread color dye over the surface, good design. When all the dye overflows, if this doesn't occur, improvements can occur. If indeed I am running where there's a substantial portion of this not overflowing into the weirs, I know that I can make an improvement in the process. It's very important. If this does not occur, I mean overflow does not occur, then improvements can be made. Now, precipitation reactions. I've been talking about this already. Let's go and draw us a picture here. Basically, I have the feed plume coming in, right? So I'm going to hit me with some highlighter. And I have the feed plume coming in. Now then, where the reaction occurs, reaction occurs around the perimeter. There's where the mixing vortices are. So the size of the job would be the area of the plume, right? And the perimeter would be characterized by a length. So the reactor volume is L squared. The reaction is occurring in L. So I have a 1 over L effect. In other words, I do have a scale effect. And the scale effect shows up as changes in particle size, right? And that's why precipitation reactions are could very easily scale dependent. This is not rocket science. It may be mysterious and it may be all magical, but it isn't that difficult. The difficulty is comes from not recognizing it. My power source is now almost deleted, and I'm going to stop right here. At the end of the day today, and Monday brings another day. So, or excuse me, this is Friday afternoon. I got to go repower up my computer and have a go at it. I'll probably continue this on Monday. Anyway, today is, I won't say what today is. Anyway, you all have a good weekend, and even though you don't know it's a weekend coming up, it's a weekend for me. I got to go home and work for the wife. Anyway, pick it up at a later date. I'm going to stop now.